Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Models Part 8 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of deformed shell model. Number 2, knowledge of Nielsen quantum number. Number 3, the effect of deformation on energy levels in nuclei. Deformed shell model. In this particular slide, we are going to introduce the basics of deformed shell model. That what is deformed shell model and what it is all about. The model is similar to shell model but has the deformed potential. It means that we have understood up to the previous lecture that nuclear shell model was successful in explaining the properties of various ground state and excited state properties of nuclei, which are basically spherical or nearly spherical. But for deformed nuclei, the shell model was not very successful. So what the people have tried basically that they in the treatment of nuclear shell model, they basically took the potential as the deformed potential, and then basically they named this model as the deformed shell model. So the model is similar to shell model but has the deformed potential. This model proposed by Nielsen unifies the single particle and collective aspect of nuclear structures. The energy of single particle states calculated using anharmonic oscillator potential. Anharmonic oscillator potential means the deformed potential, what has been considered in this particular model by Nielsen. So energy of single particle states calculated using anharmonic oscillator potential. Nielsen model Hamiltonian. How the Nielsen model Hamiltonian looks like in the deformed shell model. It is basically given by H is equal to H deformed plus C L dot S plus D L into L plus 1. If you remember the Hamiltonian for spherical shell model, then it was H is equal to H isotropic plus C L dot S plus D L into L plus 1. So now you can compare that how this Hamiltonian is different from the one that we have seen in case of spherical shell model. So here instead of H isotropic, here we have taken H deformed. Rest of the expressions are same. Where H is equal to H kinetic plus m by 2 omega 1 square bracket x square plus y square plus omega 2 square z square bracket close plus C L dot S plus D L into L plus 1. It means now we have defined the deformed potential, deformed Hamiltonian. Hamiltonian we know is the total energy of an object. Total energy means the kinetic energy plus potential energy. Kinetic energy is the same, so H deformed can be written in the form that H is equal to H kinetic energy plus V deformed. V deformed means the anharmonic oscillator potential. So first term in the expression is basically the kinetic energy term, and the second term is the deformed Nielsen potential or deformed harmonic oscillator potential plus the usual term like C L dot S plus D L into L plus 1. Deformed shell model. In this slide, we are going to discuss the details of deformed shell model. Now the z-axis in the nucleus is considered as the symmetry axis of the nucleus. Omega 1 is equal to harmonic oscillator frequency along x and y axis. Omega 2 is equal to harmonic oscillator frequency along z axis, and omega 0 is isotropic oscillator frequency. What does this mean? In the nucleus, as we have assumed that the nucleus is deformed only along one axis, it means the other two axes in the three-dimensional space, we find that the other two axes, the nuclear dimension along the other two axes like x-axis and y-axis are same, whereas the dimension of the z-axis along the z-axis are different. So this is called axial deformation. So in the similar way, if we consider the vibrations of the nucleus, then harmonic oscillator frequency along x and y axis are same. Omega 2 is equal to harmonic oscillator frequency along z axis, and omega 0 is equal to isotropic oscillator frequency. Isotropic oscillator frequency means for spherical nucleus, not the deformed one. In this case, frequencies omega 1 and omega 2 are connected to the harmonic oscillator frequency omega 0 by the following formula. Omega 1 square is equal to omega 0 square bracket 1 plus del by 3 bracket close, and omega 2 square is equal to omega 0 square 1 minus 2 by 3 delta. So it means we have made a connection of frequency of harmonic oscillator frequencies with the for the deformed nucleus with the spherical nucleus. Deformed shell model. In this slide, again we continue discussing the shell model for deformed nuclei. Now with Nielsen parameter, delta is basically the parameter which was introduced by Nielsen. Nielsen developed this deformed shell model, so the parameter was named as Nielsen parameter. So where Nielsen parameter delta is equivalent to 3 by 2 square root 5 by 4 pi into beta 2, that is very close to 0.95 beta 2. So which indicates that Nielsen parameter delta is connected to the quadrupole deformation parameter beta 2, and the relation between these two is delta is nearly equal to 0.95 beta 2. So it means if we know the deformation of the nucleus in terms of delta, we can find the quadrupole deformation parameter associated with that nucleus. As the nuclear matter is incompressible, that is volume under all conditions remain constant, so the product of the frequencies, that is omega along the 3 axis, that is omega x into omega I into omega z, has to be equal to omega 0. So it means omega 1 into omega 1 into omega 2 is equal to omega 0, or omega 1 square into omega 2 is equal to omega 0. From the shell model solution of simple harmonic oscillator, shell model solution means for a spherical nucleus. From the shell model solution of simple harmonic oscillator, h bar omega 0 is equal to 41 a to the power minus 1 by 3 bracket 1 plus minus n minus z upon 3a bracket close in terms of MeV. So these are the results that we obtained for spherical shell model. That is h bar omega is nothing but the energy, ground state energy. So it means it is given by a and is a function of n minus z, where the negative sign is used to get the h bar 0 value for proton, and the positive sign is used to get the h bar omega 0 value for neutrons. Deformed shell model. So in this case, basically the total Hamiltonian in the deformed shell model can be represented as h is equal to h naught plus delta h dash, where h naught is basically the Hamiltonian in case of a spherical nucleus, delta is the Nielsen parameter, and h dash is the deformed part. So we can consider an axially deformed nucleus as equivalent to, what does the meaning of this expression indicates? It indicates that we have considered our nucleus, or we have assumed our nucleus as axially deformed nucleus as equivalent to a spherical nucleus with a small perturbation part. So H0 is basically the spherical part, spherical nucleus part, and H dash is the perturbation part due to the deformation. So H0 is given by minus h bar square by 2m del square plus m omega 0 square r square by 2 minus c l dot s minus d l square. This is the same expression as we we have used in case of spherical shell model is the Hamiltonian of a spherical nucleus, and H dash Hamiltonian H dash is equal to m by 2 omega 0 square 2 by 3 x square plus y square minus 2z square, or H dash is equal to m by 2 omega 0 square 4 by 3 r square p2 cos theta, where p2 cos theta are a spherical harmonic of order 2 and cos theta is equal to z by r. Deformed shell model. Now in this slide, basically the labeling of energy levels in case of deformed shell model are discussed. Now in order to define, because the deformed shell model energy levels are different than the ones we obtained for spherical shell model. So we have to name them differently. We cannot name them in the same way as we have done for spherical shell model. In order to represent them or in order to label them, Nielsen basically introduced some quantum numbers which are called Nielsen quantum numbers. So according to Nielsen, the energy levels in the case of deformed shell model labeled in the way that omega, pi, n and z, lambda, where omega is the projection of total angular momentum of the nucleus on the symmetry axis, pi is the parity, n is the oscillator number, nz is the projection of the principal quantum number on the z axis, and lambda is the projection of orbital angular momentum of the nucleus on the symmetry axis. Now here in this slide we can see the picture on the left hand side where the geometrical meaning of all these quantum numbers are basically shown. Here in the picture, r is basically the angular momentum generated due to the rotation of the nucleus. So j plus r is equal to I, omega is equal to lambda plus sigma, k is equal to sigma I omega I. So various quantum numbers are geometrically represented in the figure. So here in this case, omega is equal to lambda plus sigma, omega is the projection of j is equal to L plus S on the z axis. Deformed shell model. So in this slide we are going to discuss eigenvalues of the deformed nuclei. So since we have seen that the whole discussion about the deformed shell model lies about considering the deformed axially deformed nucleus as equivalent to a spherical nucleus plus a small perturbation due to the deformation. So here, due to the deformation, if we calculate the energy associated with the deformed part of the Hamiltonian, then it turns out that the energy is delta E is equal to, is a function of n, is the expectation value of delta E is equal to the expectation value of deformed part of the Hamiltonian in the spherical basis or cylindrical basis. So when we calculate them, we have the choice that either we can find the expectation value of the deformed part, that is delta S dash, in the spherical basis or in the cylindrical basis with the wave function having quantum numbers n, l, s, j, omega. So when we calculate it in the spherical basis, then it turns out that delta is equal to 1 by 6 delta m omega 0 square into mean square radius into 3 omega square minus j into j plus 1 upon j plus 1. As for a spherical nucleus from shell model, mean square radius is equal to n plus 3 by 2 h bar over m omega 0. So 1 by 6 m omega 0 square into mean square radius is equal to n plus 3 by 2 h bar omega 0 upon 6. So if we want to see now the complete expression for the energy, or you can say that the energy eigenvalues in Nielsen model, it comes out to be as E is equal to expectation value of H0 plus expectation value of delta H dash, and the expression is E0 plus n plus 3 by 2 h bar omega 0 upon 6 delta 3 omega square minus j into j plus 1 upon j plus 1, whereas the first term on the right hand side in the expression is the energy of the spherical shell model, whereas the second term is basically due to the deformation, deformed shell model. So, from the expression on the previous slide, we have seen that the energy in axially deformed nuclei basically depends upon various things. That is, the energy of a level depends upon the deformation of the nucleus and also on the omega value, that is projection of total angular momentum on the symmetry axis. So, it means deformation removes the degeneracy with oscillator number n and split it into n plus 1 level. So, here on the left hand side in the slide, a table is given in which various nuclei are being discussed in terms of their quadrupole moment, the deformation, shell model predicted ground state spin and parity, Nielsen model ground state spin and parity, and what is the situation experimentally. For example, in the first case 19 fluoride is being discussed. In case of 19 fluoride, Z is equal to 9 and N is equal to 10. Quadrupole moment observed for this nucleus is 0.06 barn. Deformation observed is 0.05. Now, as per the shell model calculations or as per the shell model, its ground state spin and parity should have been 5/2, but since it is deformed, then according to Nielsen, its ground state spin has to be 1/2 plus, and experimentally also for fluorine 19 the ground state spin and parity turns out to be 1/2 plus. Similarly, in the case of neon 21, which has got 10 proton and 11 neutron, the quadrupole moment is 0.09 barn, deformation is 0.09. Shell model, if we predict a shell model, if we see neon 21 as spherical, predicts its spin, ground state spin and parity as 5/2 plus, whereas considering the deformation, Nielsen predicts its ground state spin and parity as 3/2 plus, and experimentally also for neon 21 the ground state spin and parity turns out to be 3/2 plus. Again, for the case of 23 sodium, which has got 11 proton and 12 neutron, the quadrupole moment is 0.14 barn, deformation is 0.11. The shell model predicted ground state spin and parity is 5/2 plus. Nielsen model predicted value is 3/2 plus and experimentally observed value is 3/2 plus. So, in all three cases, we see that the experimental observations are close to the or more or less matching with the Nielsen prediction rather than shell model prediction. So, here on the right hand side, a picture is shown in which various splitted levels of various splitted sublevels of I13/2 orbitals are given. The lowermost, so here basically I13/2 orbitals as a function of deformation are being plotted for a deformed nucleus. So, here I13/2 orbital basically splits into 7 levels with omega is equal to 1/2 as the lowest value. Omega is equal to 1/2, omega is equal to 3/2, 5/2, 7/2, 9/2, 11/2 and 13/2. So, they are basically in the increasing order of energy, whereas on the if the deformation is negative, it means if the nucleus is oblate, in this case their behavior in terms of energy is reversed, that is omega is equal to 13/2 is lowest. So, depending upon the nature of deformation of an axially deformed nucleus, whether the deformation is prolate or oblate, the behavior of Nielsen orbitals is different. Deformed shell model. In this slide, the actual behavior of Nielsen orbitals as a function of deformation is represented for protons as well as for neutrons. So, now the first picture, the Nielsen orbital, Nielsen single particle energy levels are given for protons, and you can see that orbitals basically have different behavior at different deformations. Similar conclusion we can draw for the case of neutrons. In case of neutrons also, the behavior of various orbitals varies as a function of deformation. Shell model limitations. So up to now we have seen the spherical shell model and the deformed shell model. So, and we concluded that the shell model as well as deformed shell model are helpful in determining or in predicting the ground state spin and polarities of the nuclei. Now we can see that the shell model is basically a very successful model in explaining the experimental observed data as well as in predicting various nuclear properties in ground state as well as in excited state, but it also has certain limitations. What are those limitations that we are going to study in this slide? Shell model fails to account for, especially for heavier nuclei, the spectra and or the magnetic dipole moment of excited state. It means the shell model could not explain ground state is important properties, various important properties of heavy nuclei. What are those important properties? It could not explain the spectra, the energy spectra, and or the magnetic dipole moment of excited state observed in heavy nuclei. Also, it could not account for the large observed quadrupole moment in nuclei. In some of the nuclei, the shell model predicted some quadrupole moment value as according to spin values, but experimentally observed quadrupole moment is found to vary considerably from the prediction. At the bottom of this slide, a table is given in terms of in which various nuclei are being discussed. In these nuclei, various properties have been observed and their behavior as a function of or their variation with the shell model predictions are being discussed. For example, oxygen 17. In case of oxygen 17, the proton number is 8, neutron number is 9. So we can characterize it as doubly magic plus 1 extra neutron. The extra neutron is in J is equal to 5/2 orbital. Now Q observed means experimentally people have observed Q where the quadrupole moment as -2.6 and the estimate the predicted quadrupole moment from the shell model was -0.1. So there is a factor of 20. So 20 times larger, we can say that the 20 times larger quadrupole moment is observed as compared to the predicted value. Similarly, in case of 39 potassium, which has got 19 proton and 20 neutron, we can characterize it as doubly magic minus 1 less proton. That 1 less proton or the whole is in J is equal to 3/2 orbital. For this nucleus, experimentally people have observed quadrupole moment as 5 plus 5.5, whereas the shell model predicted its quadrupole moment as plus 5. So there is a factor of 1.1. It's we can consider it, means we can say that this is more or less same. But in case of lutetium 175, which has got 71 proton and 104 neutrons, the character is between the shells. The spin is basically 7/2. The observed quadrupole moment is plus 560, whereas the predicted quadrupole moment is -25. So if we compare these two, we find that the experimentally observed quadrupole moment is 20 times that of the predicted quadrupole moment. And not only the magnitude, but also sign is also not correctly predicted by the shell model, because experimentally positive sign is obtained, whereas theoretically or according to shell model, the quadrupole moment has to be negative. In case of bismuth 209, which has got 83 protons and 126 neutrons, we can characterize it as doubly magic plus 1 proton. This odd proton basically is in the 9/2 orbital. So we can say that the ground state spin of base 209 is 9/2. Again, in this case, the observed quadrupole moment is -35 and the cell model predicted value is -30. so there is a factor of 1.1. So in these cases, these are only few cases where we have seen that the experimental quadrupole moment is not matching with what it should have been as per the shell model. So it means the shell model is limited. Shell model doesn't explain everything for nuclei. Shell model limitations. In this particular slide, we are going to study what are the limitations of shell model. Though we understood that shell model was very successful in explaining the ground state and excited state properties of very many nuclei, then came the deformed shell model, which was proposed by Nielsen and was also successful in explaining the various properties of nuclei, basically which are deformed in their ground state. But there are certain limitations of the shell model, which means there are some cases where we cannot apply the shell model. So we need to understand what are those limitations. The first limitation is failure of the shell model is due to the assumption that the nucleons move in a spherical symmetric potential. So one of the important assumptions in the shell model was that all the nucleons inside the nucleus move in a spherical symmetric potential. Second limitation is consider collective motion as it is generalized the result of shell model by considering the effect of non-spherical symmetric potential, which lead to substantial deformations for large nuclei and consequently large quadrupole moment. So students, let us summarize what we have learned in this module. We have seen that very many concepts have been discussed in this module, but now it's time for us to recap what we have learned so far. In this module, we learned number 1, Nielsen model improved the understanding of the nuclei further. Second important thing, the Nielsen modified shell model by considering deformed potential. Third important thing, the deformation removes degeneracy with n and split it into n+1 level. Also, we have learned that Nielsen model is more successful as nuclei are mostly deformed. And the last thing that we have understood is that shell model and Nielsen model fails for non-magic nuclei, as in those nuclei the potential is not spherical symmetric.